most of man's history, he has been a mere observer of the universe. Today, he stands at the doorway to space, and tomorrow, he will explore other worlds at first hand. Just one aspect of this unique experience is the difficulty man faces in returning an object from space and bringing it safely down to Earth. When a meteor strikes the atmosphere, it begins to heat through friction. The rock and metal burn up, and we see it as a shooting star. When a space vehicle takes off, it gathers speed slowly and reaches thin air before friction heat is a problem. But during re-entry, it will be reaching 15,000 miles per hour, and unless some method is used to transfer heat away, it will vaporize just like the meteor. To defy nature and solve this problem involves complex laws of high-temperature gas dynamics. But the principles can be understood by any intelligent high school student. We've called on this one for assistance.
Oh, this is basketball practice?
You've got your dates mixed again, Albert. That's better.
I was confused.
Yeah. Well, now then, Albert, the important part of a returning missile, or a spaceship, is
the nose cone.
Or more correctly, the re-entry vehicle. It's the part that contains the instruments, warhead, or human cargo.
And it's got to come back undamaged, right?
Mm-hmm. You understand the danger.
Sure. Pressure is built up because all the zillion air particles can't get out of the way fast enough. The re-entry vehicle runs into a brick wall of packed air.
Yes, Albert. Even more important, though, when a nose cone plows into the air envelope, friction generates heat more intense than the sun, enough to vaporize the cone almost instantly.
Oh, unless it's a special material and a special shape.
Yeah, heat transfer. That's the basic problem of re-entry from space. Intermediate range and intercontinental ballistic missiles were the first objects man ever had to design to leave and return through the Earth's atmosphere safely. To fashion a nose cone that would come back from space without burning up, one of the toughest challenges the Air Force ever had to face. There was an obvious solution.
They could make small-scale models and fire them up into space.
Mm-hmm. Trial and error. But there was a more daring solution, if it could be done.
To bring space down to Earth.
And that was the revolutionary concept submitted by Avco Corporation to the Air Force. To duplicate inside a laboratory, on the ground, every condition that might exist in outer space. To simulate high-speed travel at the edge of the Earth's atmosphere, the scientists turned to an unusual laboratory research tool.
A shock tube.
Instead of firing the nose cone at the gas, they reversed things and fired the gas at the nose cone.
I know about the shock tube. It works like a big gun.
All right, Albert. Suppose you explain it.
Hydrogen and oxygen are mixed here, and terrific pressure is created when they're exploded. This releases a man-made shock wave, twice as hot as the surface of the sun. The test is completed in a zillionth of a second. That's why the tube doesn't melt.
The purpose of the shock tube is to tell the scientist how air behaves when a re-entering nose cone plunges into it.
Yep, a model of a nose cone is set here, and a special camera here takes photographs at, gee, half a second, I guess.
1/1,000,000th of a second, Albert. That's why it's special.
Man, that's fast. That's space for you. Anyway, here's some real shock waves.
Through the use of the shock tube, nose cone models of every conceivable shape were tested for heat transfer, pressure, gas flow, and chemical kinetics. And gradually, the impossible became reality. In less than 6 months, the Air Force pronounced the experimental project a success. All firms involved in the Air Force ballistic missile program received the basic information from Avco's Everett Research Laboratory, and the corporation proceeded immediately to form its Research and Advanced Development Division, where the long and difficult work was begun to design, develop, and put into production a nose cone for the ICBM Titan. Meanwhile, experimentation continued. The shock tube had revealed the basic physics of re-entry. And now, to test the durability of materials, a new tool was developed, the plasma jet generator. Here, electrically arc-heated air blasted away at models at a constant 15,000 degrees Fahrenheit. Research came a new secret material, Avcoite, which promised to unlock for man the mysteries of interplanetary space.
April 8th, 1959.
Yes, Avcoite was used on the first ICBM nose cone to perform successfully and be recovered from a true flight into space. That cone was recovered not partially disintegrated like a meteor, but intact.
Boy.
And to Kendrick Wilson, president of Avco, and Lieutenant General Bernard Schriever, head of Air Research and Development Command, here was proof that the problem of re-entry from space was solved.
Yep, but that was all the past. What about now, the future? Spaceships, man!
It was the past that made the future possible, Albert. Only when the years and the money invested had resulted in a successful re-entry vehicle did we dare consider...
Returning a man from space, huh?
Yes, Albert. A satellite will be traveling at approximately 18,000 miles an hour, the velocity required to establish and maintain an orbit. The same re-entry physics will apply, except that to lessen the heating and deceleration effects on the pilot, the re-entry vehicle will come in at a shallow angle.
Hey, neat! To beat the heat.
Well, remember, Albert, an object traveling at 18,000 miles an hour has tremendous energy of motion.
Kinetic energy.
And when it crashes into the atmosphere...
I know, friction. Energy into heat. Like this. It multiplied a zillion times.
And to keep a payload safe, to keep a man alive, that heat must be dissipated.
Like scattered.
Radiated.
Cool. I mean crazy. How?
Well, you know, Albert. Draw. First, a re-entry vehicle might have a heat sink surrounding its payload. Special material...
That would soak up heat like a sponge.
And second, ablation, like the first ICBM nose cone recovered by the Air Force.
Yep, the outer surface made to melt, absorbing heat that way and flowing away from the nose cone as a gas. So the nose cone handles the heat. What about slowing down something with a man inside?
Well, there are various ideas about that, Albert, depending on what recovery method is used. For instance, one technique is the Avco drag brake. This is a kind of parachute which radiates heat away during re-entry and helps to slow down and guide the vehicle to its landing.
Like an umbrella, a skyhook.
Oh, that's the principle, but the other way around in this case, Albert.
Hey, terrific!
Yes, this is just one of the ideas being developed to assist our country's space program. Other ideas in work today are secret. But with the speed of accomplishment necessary in the race into space, These secrets may be in your newspaper any morning.
Say, I got a few questions to ask.
I'm afraid they'll have to wait, Albert, until graduation. And then perhaps you'll qualify as a space explorer yourself.
And maybe even travel to other planets.
More than likely, Albert. But until that time, it's good to know that Avco and many other firms are assisting the Air Force and the civilian organization, NASA, the National Aeronautics and Space Administration, in their space programs. And that they are exploring every possibility to safeguard the first American who, after a flight beyond the atmosphere, will be coming down to Earth.